All right, welcome to The Explainer. Today we're going to break down a concept that's, well, it's absolutely foundational to ecology. And for any life science student, especially if you're prepping for the CSIR-NET exam, this is a super high-yield topic: Lindeman's trophic-dynamic concept.
So let's just dive right in. This image here, it gives us a fantastic overview of what we're talking about today. See, back in 1942, a guy named Raymond Lindeman gave us this brilliant quantitative way to see how energy moves through an ecosystem. It's not just about who eats who, it's about following the energy.
You know, before Lindeman came along, ecology was, well, it was mostly about describing things. He completely changed the game by saying, hey, let's look at an ecosystem as one big integrated unit that processes energy. I mean, this was a huge shift in thinking. Okay, so here's the absolute key point, the thing you have to remember. Energy flow is a one-way street. It starts from the sun, gets captured by plants, and then moves on up the food chain. And at every single step, because of the second law of thermodynamics, some of that energy is lost as heat. Think about it. Nutrients like carbon or nitrogen, they get recycled. But energy? Nope. It's a single-use resource.
And that brings us to a really important way of looking at this. It's all about function. A trophic level isn't just a species name, it's about the job an organism does in this energy flow assembly line. This also brings up the decomposer paradox, which, by the way, is a classic exam question. Where do things like fungi and bacteria fit in? Well, everywhere. They break down dead stuff from all the levels, so you can't just stick them in one neat little box.
All right, let's get to the real heart of Lindeman's concept. It all boils down to this one simple, powerful number that explains so much about how the natural world is put together.
That's it. That's the magic number you've got to lock in your brain, not just for your exams, but for really getting ecology. 10%.
So what does that mean? It means that on average, only about 10% of the energy from one level actually makes it into the body of the next. And that right there, that massive inefficiency, is the answer to that classic exam question. Why don't we see food chains that are like 10 levels long? There's just not enough energy left to support a sixth level.
So that's the big question, right? If only 10% moves on, where does the other 90% vanish to? And figuring this out it's fundamental to understanding how ecosystems work. Okay, and this slide just lays it out perfectly. See, that huge chunk, that 90%, it's not just disappearing. The organism is using it to live, to move around, to breathe, to stay warm. All of that is powered by that energy. A lot is also lost as waste. Respiration alone is the biggest energy drain. So only that tiny little slice that becomes actual body mass is up for grabs for the next predator.
So let's take this rule and see how it actually builds the structure of pretty much every ecosystem out there. We're talking about ecological pyramids. The official term for this, the one Lindeman gave us, is ecological efficiency. It's just a formal way of talking about that 10% transfer. You can think of it as the currency of life. It literally dictates the entire energy budget of an ecosystem.
Let's look at some actual numbers. In a classic grassland like this one, the math is crystal clear. If the producers start with 10,000 kilocalories of energy, the primary consumers get just 1,000. The secondary consumers get 100, and the poor tertiary consumers are left with only 10. And take a good look at this table, because this is exactly the kind of data interpretation question you'll see, especially in Part C of your exam.
Now this brings us to what is pretty much an absolute law in ecology. You see, sometimes you can get a weird upside-down pyramid of numbers or biomass, like imagine one giant tree supporting thousands of tiny insects. But a pyramid of energy? No way. It can never be inverted. Because you're always losing energy at each step, the base has to be the biggest. That's a critical concept, especially for those statement validation questions.
All right, let's dig a little deeper now. We're going to look at some concepts that are really going to help you with those trickier, more challenging exam questions.
So this is a big one, especially for those match the following type questions. What's the difference between Lindeman and Elton? Just remember this. Lindeman is all about function and energy flow. Elton? His earlier work was about structure, counting things, weighing things, numbers and biomass. It's a crucial difference.
But we also have to remember this is a model, right? It's a simplification. And a great critical thinking question for an exam is to ask about its limits. For one, that 10% is just an average. Real food webs are way more complicated than simple chains, and this model often doesn't give enough credit to the huge role of the detritus food chain, all that energy flowing through dead stuff.
So you have to ask, why is this idea from way back in 1942 still so fundamental? Why is it the bedrock of modern ecology?
Okay, here it is, your rapid-fire revision slide. If you're cramming, this is what you need to know. Lock this in. Lindeman, 1942. The big idea? The 10% law. The flow? One-way street, always unidirectional. The result? An energy pyramid that always stands upright. Got it?
At the end of the day, the reason this whole trophic-dynamic concept is so powerful is because it's the foundation for everything. It lets us explain energy flow, figure out the productivity of a whole landscape, and even start to understand how stable these communities are.
And that really brings us to our final thought here. Lindeman didn't just give us a rule for food chains. He gave us a new way to see the fundamental logic of how life organizes itself. When you really get this one simple rule, you're not just learning a fact for an exam. You're getting a peek into the engine room of nature itself.